Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our modern C++ series. In this lesson, we're going to continue talking about STL data structures, this time talking about a container adapter, the priority queue. So if you've been watching this series and you've been subscribed already, like you should be, then you've already seen the stack and the queue where we left off last time. And priority queue is, we can think of another sort of specialization of queue, this time with sorted order. Now, let's go ahead and talk about what a priority queue is, but first we're going to look at the CPP reference, and then we'll draw out the data structure and do a few examples so you can see how to use it. All right, so from the CPP reference here, let's go ahead into containers, libraries, and down to priority queue. So what is a priority queue? Well, it's again a container adapter, meaning that we can change the underlying storage. And again, it's enforcing some sort of policy or restriction for how this particular data structure can be used. So the underlying data structure could be something that we've learned about by default, for example, a vector, but we could maybe change this to some other data structure behind the scenes that allows us to store and access our data in a particular way. And that might impact the performance based off of what operations we're doing. But anyways, let's get back into the priority queue. So again, that's what it means to be a container adapter. And it provides constant lookup time of the largest by default, or we could change that to be the minimum. So this is by default a max priority queue. And it gives us insertion and extraction, so removal from this queue in logarithmic time. So again, this idea of a priority queue sort of builds on top of the idea of a queue, but in the sense that if we have customers with some priority, for example, let's think about just a real world problem like airlines, for example. If you have folks that are flying first class versus the economy class, they have a higher priority. So we'd want to be able to sort those customers and access them with the first class passengers first, who would board the airplane first, just as an example. So anytime you have some data that has some sort of priority, at an operating system level, this might be some process that has a higher priority, for instance, it needs to run more frequently, maybe a security system, for instance. And that's how an operating system can decide, how often to run some different process. So those are just some examples in the real world where you might use priority queues. And again, you could use this priority queue data structure also to implement different types of sorts, things like heap sorts, for example. I'll talk a little bit about priority queues implementation momentarily, that it's probably implemented as some sort of heap-based data structure in order to get this logarithmic insertion and extraction time here. Okay, now what are some different things that we can do with priority queue? Well, one is we need to decide what the priority is. And in the case of an integer, for example, for storing this container, by default, it's just the largest element. But if we have our own data structure that we want to implement, then we need to write our own compare function, which I'll show you how to do here, okay? All right, so as mentioned, priority queue is very similar to just managing a heap here. Again, what type of heap is it? A binary heap or Fibonacci heap or these types of things? We'll have to actually look at some source code. In fact, if we open up GCC here and look at the library here, priority queue, which is in the, let me go ahead and show you the queue header here. And let's go ahead back down to priority queue. We can look at the implementation a little bit here. So again, it's a standard container. It sorts the contents of its elements, but it sorts them to the extent that you have just the largest element at the top by default here. All right, so that's just a little bit here about the priority queue here. And let's just go ahead and look through here briefly. You can see some of the different operations, the compare that we're going to override here, and how to, again, create our priority queue. And it looks like we see that it is, in fact, using some of the make heap operations that are part of the standard library. So it's pretty safe to assume here. And let's actually look here at our make heap, standard make heap. And let's go ahead and see if this is if it tells us if it's a binary heap or Fibonacci heap or some different things here. Binary. Fib, I guess it doesn't tell us, and we'll look into heaps later on, but that's the basic idea, that it's a heap-based data structure. Now, if all of this I'm saying to you is a little bit weird, what are heaps and so on, the basic idea, and again, let's think about this just with integers, is if I have some collection of data here, some numbers here, 73, 52, the number 1, for instance, and I want a max priority queue, I could use behind the scenes a data structure known as a max heap, which will sort these by keeping the largest element here. And let's go ahead and add something here like 42. So again, if I'm just going to sort of add these one at a time here, I could have some sort of, I'm going to represent this as a tree here, 42 here. So that's the first thing that's inserted. And then 73. Well, usually what happens is I insert this into my actual data structure here. Again, if it's a binary heap, I just sort of insert it at the lowest level here. And then we decide, well, once I've inserted it into this tree, I do a comparison between 42 and 73 here. And I find out that 73 is larger. So now I update my tree, and I'll have to just scratch this out to have 73 at the top and then 42 at the lower level. Then if I add 52, I simply come into the next spot here, do that same comparison and see if it needs to be promoted, and so on. And then let's go ahead and add 1 here. And I'll add that into my structure here. And again, we can do this sort of comparison here. 1 is smaller. So if I just sort of look at the different levels here in this data structure behind the scenes, everything on this level is smaller than what's on the level below it. You can read about the various heap properties for whatever heap you're implementing, but that's the basic idea. So the tallest or the greatest element, since there's only 1 at the top of the tree here, must be the maximum. Okay, so this is what I can then extract. And then when I extract this, if I remove something from my priority queue, again, what's the most important thing here? 73. Then I rebuild my heap. And there's various algorithms, right? Usually you take the bottom of your tree, put it to the top, just show you here, 1, 42, 52, and then you go through that same process again, comparing your items and promoting to the top eventually so that you get a swap here. And then your new heap would end up being 52, 1, or 52, 42, and 1. So something like that here, right? Where everything at this top level is greater. So that's the basic idea here, okay? Of our max heap. We get the greatest element at the top. All right, so enough on that. The great thing is this is built into the standard template library. Implementing a priority queue is probably a good exercise for you to do, maybe for a interview or just a data structure to know about in general. But let's go ahead and see what's available in the C++ library by looking at priority queue and actually using it, and actually looking at if we have something that isn't just an integer. But let's start with integers first for priority queue. And again, this is a data structure that's been around since C++ 98. It's been available for quite some time. And you'll see that it looks pretty much the same as the queue that we looked at previously with push and pop operations here. So let's go ahead and include queue here, which will give us access to priority queue. And let's go ahead and create the priority queue. And I'm just going to put in integers for now. I'm just going to call it priority queue as such. And that should create our priority queue. Let's go ahead and push in some values, 32. And let's go ahead and do 33 and 31 here. Okay. And now let's just go ahead and say, while our priority queue is not empty. So again, we're checking, is it empty? So we want to say not empty. That's sort of the pattern. I wish they would have named this is empty to be a little bit more clear. But then we're going to do the same sort of operations that we've been doing. If you've been watching this series, I'm just going to pop off the elements. But again, pop only does one thing here. It just removes the top element, doesn't return a value. So for that, we want to first look at the top or the most important element in our priority queue and store it. So I'll just call this T for our priority queue top. And then let's just print it out. So ordering, we'll print out T there. And we should see these numbers printed out in order, the max, the greatest, 33, 32, 31 here. Okay, so let's go ahead and give this a compile. No mistakes. Give it a run. And we see our ordering here, 33, 32, 31. So every time we remove something, that's a constant time operation. So let's go ahead and see, or I should say, every time we just look at something, that's a constant time operation. So we have top here, constant. And then every time that we're removing something, pop, we have to restructure. So we have this sort of heap property here. So you'll see that's a logarithmic operation here. Okay, so effectively this is one way that you can do a heap sort if you've seen that algorithm here where we're removing things n number of times and then rebuilding the structure in logarithmic time. So n times log of n. Okay, so just a little bit of algorithms there for you mixed into here, a little bonus. So anyways, that's priority queue. But let's go ahead and see what happens if we have our own data structure here. So let's create our own struct here. And again, I'm just going to make up something here. Let's go ahead and say edge, for instance. And let's go ahead and say I have an edge. It's got, I'm just going to give it some values, vertex 1 and vertex 2 here. And we could assume these are just integers that index into something. But the point is just to have some non-trivial data structure here. Let's go ahead and set these up here. I'll create a constructor. And basically what I want to show you that we're going to do here is just create a custom compare function like we've done many times before here. And that way we'll be able to actually sort these edges here. Okay, so this is sort of experiment 1 here. I'll comment out here. And then let's go ahead and set up experiment number 2. Okay, now let's go ahead and do standard priority queue. And this time I want to use our edges. And you might use this for something if you're in geometry of comparing edge lengths or distances of some manner here. So anyway, it's just something that's on my mind here. Let's see, I can compile this. It seems to run fine, so no mistakes quite yet. But let's actually start using our operations. So let's actually push in some edges here. So edge E1. I'll give it a value of 1, 1, edge E2, and edge E3 here, okay? And we'll give them, let's just push in these edges into our data structure. And let's see if this, how this fares here. Doesn't work quite yet, okay? So at this point, once we start using our data structure, it's gonna say, hey, you know, we don't know how to basically compare this custom data type here in your priority queue. Okay, so that's where we have to go to the top here and implement this compare operation here for our priority queue. Okay, let's see if there's actually an example here. Actually, there are a couple of examples showing us how to use this struct here. And again, the compare, basically we need a functor, and they're doing this example with a sort of anonymous struct here. Where I need to be able to compare something. So this is the function that needs to be called. I need to return a true or false value. And I need to know how something is greater than or less than something else here. Okay, so let's go ahead and write an edge compare function. So struct, I'm just going to call edge compare. Okay, we need a Boolean value. I'm overriding operator here. And I'm comparing 2 different edges. I'm going to compare them by reference so that it's quick. Edge 1. And edge number 2. And let's see here. We might need to make this const and maybe I'd probably make it no except here. It looks like it's just const here. So we'll go with that. And then I'll return if E1, well, let's just compute something here. E1 sum equals E1 V1 plus E1 V2. E2 sum is E2.v1 plus E2.v2. I mean, ideally, you'd probably want to do this for like edge length or something. Okay, you could add another property here. If we've created an actual vertex, if you're thinking in geometry, that would be what you'd want to do. But I just want to return E1 sum less than E2 sum, and that'll tell me, you know, the compare here. Okay, and I'm looking at this here, you know, I'm comparing less here. Okay, that's what I need to drive here. Okay, so let me see if I made any compile errors, and then I'll actually add that into our template here. Okay, it looks like we're getting the same error here, so now I'll add into our priority queue here, and that will be the third parameter here. So I need to pass in the container. I'm going to use a vector of edges as the underlying data structure. We can change that around. And then edge compare. And let's give that a try here. So I need to do a few things here. One, include vector. And then let's go ahead and parse through these error messages. in a moment here. So let's see if that helped us out. Okay, so far so good. And edge compare, let's see what I need to do here. Looks like I just made a little bit of a syntax mistake, which is probably blowing things up. Again, you've always got to look at the start of your error messages for these types of things here. E2. Okay, that's looking a little bit better. All right, now it's looking like we're good here. So now if I run this program here, let's see if I push in a bunch of edges, and let's give you a view of all the source code just so you can see what we did here. Let's go ahead, and again, I want this just to fit on one screen for you. I don't recommend putting all these on the same line. But essentially what I want to do here is, let's go ahead and just say, while edges, while it's not empty, let's go ahead and look at the top edge. The top edge equals edges top. And again, this is edges.empty here. And then we'll go ahead and pop off our edge. Let's see, what did I do here? Missing one parenthesis. And that looks like it's working here. And then just to make things a little bit easier, and I think you've seen me do this in some other videos here, we could write a little print function. Let's just make our life easier. You could make our friend function to this actual structure here. And I'll actually do that here. Let's not leave any stones unturned, so to speak here. So usually one way you can do this, again, with the O stream, basically overriding the operator, the stream operators for doing this. And we've got to talk about this on the series, so again, it's not as much of a mystery here. So basically what I'm doing here is I need to take in from the stream operator. This is sort of the left side of the equation. Anytime you see this one, we're going to print something out. This is the data type here for our edge. And then what we're returning, this stream here, is just going to be, you know, OS. Again, this is the reference. So for the left side of this equation here. And then the properties that we want here. V1, and let's put a little comma here, E.V2. And I'm not going to put any end lines or anything, but that's the basic idea. And then usually the thing that folks will do, again, is they'll make this a friend function, so you can access the private members here. So again, depending on how much control you have or whatever, that's what we'll do here. So again, I'm just typing out this same thing here again here. Okay, let's go ahead and in a moment see how good I am at typing, if I made any mistakes here. Yeah, it looks like I made a couple here, so let's see what happened. Too much of a copy and paste here. Typing out operator instead of O stream. That's what I get for talking and typing. Doing this here. O stream. Let's go ahead and try to fix some of those errors. All right, looks like we're in action here. Okay, so now we just have a handy function to print things out. That's the purpose of that. So then when I actually print out this priority queue here, we'll figure out, you know, 3 plus 3 is 6, 2 plus 2 is 4, 1 plus 1 is 2. So those are the values we're using to figure out what's the most important edge, and now it has some criteria to actually sort by. So now if I actually just do something like this and print out the top edge, we understand how to print out edges. I can compile this because we understand that this is an operator, just like plus that we're overriding, right? This is the left-hand side of the equation here with the OS stream, and the right-hand side of the equation is top edge in that print stream here. And now if I actually run it, again, 3 plus 3 is greater than 2 plus 2, which is greater than 1 plus 1, which again is our comparator function here. All right, so there we have it with a custom structure with priority queue. I think the only thing to show you now is if we want to change the underlying data structure from a vector, we can do that as well. So let's go ahead and take a look here. And here are containers. Again, because this is a container adapter, let's see. So in order to do this, we need operations like front, pushback, and popback, for instance. So vector satisfies this, including vector bool. Ooh, that's interesting. We might have to talk about that sometime. And then a deck also satisfies this. So if you really want to, let's do this as a deck here, just to do something different. And then we'll need to perhaps comment that out. And let's include deck here, double-ended queue, which we've talked about on this series. Again, just to show you, again, you could use a different underlying data structure, and you might choose to use different underlying data structures for various performance reasons, depending on how often you're inserting, if you're doing it sort of in bursts, or what you would like to do. All right, folks. So anyways, that is the priority queue. We did it with a integers as well as a custom data structure here to show you some different criteria for how we can do things. Again, very useful computer science data structure to know about, usually implemented in some sort of heap. I sort of explained very quickly a binary heap for you. That's it. So again, that's the last of our container adapters here. Check out the series if you miss stack queue or priority queue otherwise. And it's a good idea if you can visit my website and sign up, and you can track your progress. Same lessons here for free on this series, so that you know which of the STL series have you actually watched, and then you can kind of check them off, which is nice to mark your progress. So anyways, folks, that's it for this lesson. Thank you for making it this far. If you've been enjoying this, make sure you subscribe or give it a like. And with that said, thank you as always for your time and attention. I'll look out for your comments below, and see you in the next one.